Hello everyone, thank you for being interested in this video. My name is Jizhong. I'm an associate researcher in geophysics in Tongji University. Previously, I was a research fellow in National University of Singapore. I'm going to talk about the application of least squares reverse time migration with subsurface offset extension to vertical seismic profiling data. This is a collaborative work with Dr. Jingjing Zong, Professor Arthur Chen, and Assistant Professor Elite Li from National University of Singapore. My talk consists of these 4 parts. In the introduction part, I will talk about the motivation of this research. In the methodology part, I will give a short review on how to implement LSERTM mathematically. Next, I will use the simple lead model and the SIM model to perform LSERTM with both surface seismic data and VSP data. Detailed comparisons will be illustrated in this part. Finally, I will give a conclusion of this research. Let's first go through the introduction part. I would like to begin by this cartoon illustration for surface seismic survey and the VSP survey. In surface seismic survey, both sources and receivers are deployed on the surface. In the VSP survey, the geophones are deployed inside the borehole while the sources are excited on the surface. From this figure, we can see that the wave pulse in the VSP survey is much shorter than that in the surface seismic survey. As a result, the VSP data have less energy attenuation than the surface seismic data. Thus, higher resolution images can be expected from VSP data. This figure shows the comparison between the surface seismic image and the VSP image. Please note the higher resolution and more details in the VSP image. Although the illumination area in the VSP image is much narrower than that in the surface seismic image. These illustrations demonstrate that VSP has its distinctive acquisition geometry and can provide valuable information for seismic exploration. However, in field data application, velocity errors are inevitable in velocity model building because of the coherent noises in the seismic data. The simplifications we have made in physics during the processing workflow and the oppositeness of the inverse theory. Due to this fact, it is a good choice to utilize LSERTM because there is merit of fitting the observed data even when significant errors are present in the migration velocity model. LSERTM has been actively studied for surface seismic data in academic research, but it is never reported with application to VSP data. Here comes the question that, is there any difference in the behavior of LSERTM for the VSP data and the surface seismic data? We are going to answer this question in the following part. In the methodology part, I will talk about some details in implementation of LSERTM. This is the extended image condition. Here, MMIC is the migration image. D is the observed data. XS is the source location. XR is the receiver location. FST is the source wavelet function. Jx minus h xs tau is the Green's function from xs to the subsurface point x minus h. And Jx plus h xr t minus tau is the Green's function from xr to the subsurface point x plus h. When the migration velocity is accurate, the source side view field and the receiver side view field will meet at the same location at the same time. When the migration velocity is inaccurate, there will be a distance between the sunken source and the sunken receiver. The extended fault-bound modeling is the adult of the extended image condition, where the data and the migration image are interchanged. Here, U is the fault-bound model data. The rest symbols are the same as in the previous slides. LSERTM is generally formulated as minimizing the L2 norm difference between the model data U and the observed data D. This objective function can be iteratively solved with the conjugate gradient algorithm. The above equations are the same for the surface seismic survey and the VSP survey. However, it is not necessary that the behavior of LSERTM is the same for these two surveys. Let's use some numerical examples to demonstrate the behavior of LSERTM for the VSP data and the surface seismic data. We first apply LSERTM to a simple lead model. There are in total 77 sources on the surface with a source spacing of 50 meters. For the surface seismic survey, there are 401 receivers deployed on the surface with a receiver interval of 10 meters. For the VSP survey, There are 81 receivers at x equals 2,000 meters in distance from z equals 200 meters to z equals 1,000 meters at depth. The receiver interval is 10 meters. With this simulated model, I will first show the illumination difference of surface seismic data and VSP data. Next, I will compare the kinematics of the subsurface offset gathers and the angle gathers. Then I will illustrate the difference in the stackability of the extended images. We first perform LSERTM with tracked migration velocity model. The front panels show the migration images at h equals 0. It is very clear that the VSP data have much narrower illumination area than the surface seismic data. The red panels show the subsurface offset common image gathers at x equals 1,800 meters. The subsurface offset range is from minus 100 meters to 100 meters, as denoted hx here. For the surface seismic survey, most of the entries in the subsurface offset common image gathers are focused at h equals 0. However, in the VSP survey, the entries in the subsurface offset common image gathers are distributed along lines with slopes. We cannot tell whether the migration velocity model is accurate or not. We then transform the subsurface offset common image gathers into angle domain common image gathers using slant stack. Since the migration velocity model is correct, the events in the angle gathers are flat for both surface seismic survey and the VSP survey. However, only positive angles are present in the VSP survey. This is because the subsurface image points are on the left-hand side of the receiver line in the VSP survey. This is the recap of the cartoon illustration of the VSP survey. It is obvious that only one side of the receiver line is illuminated by source receiver pairs. This is the reason why only positive angles show up in the angle gathers in the right part. We then extract the subsurface offset common image gathers at x equals 2,200 meters. The subsurface offset range is from minus 100 meters to 100 meters, as denoted as hx here. In this case, the subsurface image points are on the right-hand side of the receiver line in the VSP survey. As in the previous case, most of the entries in the subsurface offset common image gathers are focused at h equals 0 in the surface seismic survey. However, in the VSP survey, the entries in the subsurface offset common image gathers are still distributed on lines with slopes. In addition, the slope information is different compared with the previous case. These are the angle gathers transformed from the previous subsurface offset common image gathers. The events in the angle gathers are flat, indicating that migration velocity model is correct. However, in the VSP survey, only negative angles show up because the subsurface image points are on the right-hand side of the receiver line. We then perform LSERTM with incorrect migration velocity model. The velocity errors are 10%. The front panel shows the migration images at h equals 0. For the surface seismic survey, the horizontal reflectors are pulled up due to the slower migration velocity model. However, for the VSP survey, the reflectors in the migration profile become tilted. More distortions can be observed from the VSP image, although the migration velocity errors are the same for both the VSP survey and the surface seismic survey. This indicates that the VSP data are more sensitive to the velocity errors. The red panels shows the subsurface offset common image gathers at x equals 1,800 meters. The subsurface offset range is from minus 400 meters to 400 meters, as denoted as hx here. Downward curvature appears in the surface seismic survey because of the slower migration velocity model. However, the behavior of the subsurface offset common image gathers in the VSP survey is significantly different from the surface seismic survey. We cannot follow the experience from the surface seismic survey to tell whether the migration velocity model is accurate or not for the VSP survey. These are the angle gathers transformed from the previous subsurface offset common image gathers. The events in the angle gathers are curved up, indicating that migration velocity model is slower. In the VSP survey, only positive angles show up because the subsurface image points are on the left-hand side of the receiver line. We then expect the subsurface offset common image gathers at x equals 2,200 meters. The subsurface offset range is from -400 meters to 400 meters, as denoted as hx here. In this case, the subsurface image points are on the right-hand side of the receiver line in the VSP survey. As in the previous case, downward curvature appears in the surface seismic survey because the migration velocity model is slower. However, in the VSP survey, we could not find similar curvature information as in the surface seismic survey. The subsurface offset common image gathers are then transformed into angle domain common image gathers using slant style. The events in the angle gathers are curved up, indicating that the migration velocity model is slower. In the VSP survey, only negative angles show up because the surface image points are on the right-hand side of the receiver line. In previous slides, we have shown that there are significant differences in the behavior of the subsurface offset common image gathers and the angle domain common image gathers. Due to these significant differences, we should be careful when adopting the successful numerical experiences from surface seismic data to VSP data. As an illustration, we apply the image enhancement strategy we have proposed for surface seismic data to the VSP data. In our previous study, we have shown that we can stack the subsurface offset extended images along the subsurface offset axis within the half-wavelength constraint. The resulting image is in better quality than the image at the zero subsurface offset and the image from conventional LSERTM, especially when large errors are present in the migration velocity model. The left shows the stacked image for the surface seismic survey, and the right part shows the stacked image for the VSP survey. This is the case for the correct migration velocity model, and this is for the incorrect migration velocity model. As you can see, the image qualities become much better after stacking for the surface seismic survey. However, for the VSP survey, the image quality degrades after stacking along the subsurface offset axis. These results suggest that it may not be suitable to directly apply the imaging algorithms developed for surface seismic data to VSP data. We then apply LSERTM to the same model. There are in total 30 sources on the surface from x equals 100 meters to x equals 3,000 meters, with a source spacing of 100 meters. For the surface seismic survey, there are 438 receivers deployed on the surface with a receiver interval of 20 meters. For the VSP survey, there are 126 receivers at x equals 1,500 meters in distance, from z equals 1,500 meters to z equals 4,000 meters at depth. The receiver interval is 20 meters. The migration velocity model is built by applying a 21-grid Gaussian smoother to the true velocity model and scaling with a factor of 0.9. The bulk velocity errors are 10%. These are the LSERTM results. The front panels show the migration images at h equals 0. For the surface seismic survey, the migration profile is dominated by high amplitude, low wave number noises in the shallow part. For the VSP survey, most imaging energies are focused on the salt body, although the structures are not well resolved. The red panels show the subsurface offset common image gathers at x equals 1,000 meters. The subsurface offset range is from -600 meters to 600 meters, as denoted as hx here. In this case, the subsurface image points for the VSP survey are on the left-hand side of the receiver line. Since we have used the slower migration velocity model, downward curvature appears in the surface seismic survey. However, we cannot find similar curvature information in the VSP survey. The subsurface offset behavior is quite different. We then stack the extended images along the subsurface offset within the half-wavelength constraints. The left part shows the surface seismic image. The image quality becomes much better when compared with the image at zero subsurface offset. The high amplitude, low wave number noises are effectively reduced. The sedimentary structures are clearly resolved. The red part shows the VSP image. It seems that the imaging of the source body is enhanced. However, it is not easy to track the sedimentary structure information. So this image cannot be regarded as an improvement from the zero subsurface offset image. This result further indicates that the direct application of imaging strategies from surface seismic data could not provide satisfactory results in VSP survey. To conclude, we have applied LSERTM to VSP geometry. LSERTM maintains its merit of fitting the data in VSP survey. However, the behavior of LSERTM shows significant differences in VSP data compared to surface seismic data. Because of these significant differences, when we apply the successful numerical experiences from surface seismic data to the VSP data, we could not get satisfactory results. Future work will focus on designing imaging strategies suitable for VSP data. This is all of my talk. Thanks again for your attention. If you have any comments and suggestions, please let me know through this email. Bye.